Okay, so Bronsted-Lowry came up with this definition of an acid that's a little more in depth than what we've been talking about, where an acid is H plus and a base is OH minus. So Bronsted-Lowry said an acid is anything that can give up an H plus. So in this situation, H3O, which is what this is, H3O plus, is giving up H plus and acting as an acid in that situation. This is why amines, nitrogen compounds, are considered bases, is because they have this lone pair here that allows them to accept a proton. So that lone pair is there, and here comes this H, and that H kind of goes on there like a hat, and then the nitrogen has accepted that H plus. So basically, what Bronsted-Lowry were saying is, why is OH minus the only base? Why is that the only thing that can accept an H plus? Other things can accept an H plus, like amines and whatnot. So that is the Bronsted-Lowry definition, that an acid is a proton donor and a base is a proton acceptor. So when we have a situation like this, we have what we call a conjugate pair. And the conjugate pair are similar to each other because of the H. So here is water, and water has an H, an O, and another H. And in the process of going to OH minus, it loses one of those H's. And the NH3 gains that H, right? So now this went from having 3 H's to having 4 H's. So in the process of this, that nitrogen ended up gaining an H plus, sort of as a hat. This lost its H plus hat, and this gained it. And so at the end of the day, this was an acid, and the NH3 was a base because it accepted that H. Now that it has the H, the NH4 is an acid because now it has this hat, right? It took on the hat. This had the hat. So if I rewrite this like this, so H, right? So here's the hat here. And then it gave its hat to the ammonia. And now the ammonia has the hat and the water doesn't. So basically, that's the deal. So the conjugate pair is the acid and the base it becomes after it gives up the H. And the base is what picked up the H, and its conjugate acid is what has the H now that it picked up the H. So it's sort of like a game of tag, right? So here's the H, and here's the amine, and then it tags the amine with the H. So now the amine is it, right? So this is now it in the tag terms, right? So that's like, that's sort of, if we're, sort of like Pennywise, right? So that's it. So this is now it because it has the H, it has the hat, right? And then when it goes back the other way, now this has the hat. So this can act as an acid when it has the H, and this acts like the acid when it has the H. When it's on this side of things, we call it a conjugate. And when it's on this side of things, we just call it an acid. So this would be the conjugate base. And this would be just the base because it's on this side. So on this side of the reaction, it's an acid base. On this side, it's a conjugate. All right. So at the end of the day, when we look at this, right, this had the H and this didn't. And so now this has an extra H. Here's the hat, right? So this one had the hat. And then it gave it to this thing. And now this has the hat. So this is the conjugate acid. And it got that from the acid. And after something that's an acid loses its H, it becomes a conjugate base. And then this was the base because it accepted the hat. So you're basically going to need to identify the acid and base on this side and then the conjugate. So on the reactant side, you need to figure out the acid and the base. And then on the product side, you need to find out the conjugate acid and the conjugate base. So the last thing I wanted to discuss is the idea of equilibrium. So we had discussed this before, and this thing is in my way. So I need to be able to hit that. All right. So equilibrium doesn't mean the reaction stops. As you can see, this reaction is going, but what happens is for every red one that turns green, there's a green one that turns red, and the ratio is pretty much staying the same here as 21 and 12. So when I'm asking you about equilibrium in the assignment, I'm basically saying which side of the reaction is favored. So if we freeze this, can you see how A, the reactant side, has more particles than B, the product side? So at the end of this equilibrium, the reactant side is favored. So A, the side of the green, is favored because there's more dots on this side than that side. And that's what I'm asking you to do in that part of the assignment where we talk about equilibrium. One side or the other is going to be favored. So we can favor the other side by doing this. I've lost some of my things, unfortunately. But if we make the activation energy smaller, now I've favored B. So if we freeze it here, it's easier for things to be B than A. So now the number in B is greater than A. So in this case, we would say this is favored. This side of the reaction is favored because it has more products. And that is all I need you to do for today.